Hello, I am Jordan Kushner, and I'm going to be going over double number representation in binary for Professor Al-Naji's CSM145 class at Moorpark College. So what I'm going to be going over in this video is fixed point notation and floating point notation. I'm going to go over what they are, and I'm going to represent a number in each notation, and then I'm going to compare the advantages and disadvantages of the two at the end. So what is fixed point notation? In fixed point notation, the decimal numbers are represented with a fixed number of bits. That means that there's a certain number of bits and that number does not change. In those number of bits, the binary point is at a specific location, and that is also fixed. So again, that will not change or will not move. The binary point is like a decimal point, but in binary, it's called the binary point. So with fixed point notation, it requires us to have two parameters. We need to know the width of the representation, so how many bits we have overall, and then the location of the binary point. So how many fractional bits, numbers after the binary point, and how many exponent bits, numbers before the binary point. So the notation is going to look like this here, and this is going to be a number, and this is also going to be a number. So if it looks like this, it's fixed 8,4. It means it's going to be in fixed notation, it's going to be 8 bits wide, and there's going to be 4 bits reserved for the fraction. Now I'm going to represent a number in fixed point. I'm going to represent 1.23, given that it's 8 bits wide and there's 6 bits after the point. So basically, we want to convert our number to binary with our first sign representing the sign. So convert 1.23 as such like this. We see 1 goes into 1.23, and then for the 0.23, we have the numbers after the point. We have 1 here, 1 here, 1 here, 1 here. If we add up all the points, we get a value that's pretty close to 1.23. Then we take this table, we put it all together, and then we get this number as our fixed point representation of 1.23 in this bit pattern. Now, what is floating point representation? Floating point representation is another way to represent double numbers. The number of bits before and after the binary point is dynamic, so this allows us for more precision with larger and smaller numbers. The exponent portion of the number represents the whole number portion, and the mantissa represents the fractional portion. So again, the part after the binary point. The first bit always represents the sign of the number, so positive or negative. For positive, it will be 0, and for negative, it will be 1. And then we calculate the exponential bias, which I'll go over in the next slide, as 2 to the k minus 1, so 2 to the number of bits in the exponent portion minus 1, and then we add the sign, so 1 or negative 1 times the number of bits. And then this is used to determine the exponent portion of our number floating point, and k represents the number of bits in the exponent portion, as I previously said. So here's how we would represent a number in floating point if we wanted to represent the same 1.23 in what is called single precision, which is 32-bit floating point. Double precision would be 64-bit. So first we want to convert 1.23 to binary, and it's easier to think of it as converting 1 to binary and converting 0.23 to binary separately, and we also want to figure out our sign value. So here we can see 1.23 is positive, so our sign here is going to be 0. Then we want to convert our 1 to binary. 1 in decimal converts to 1 in binary. It just happens to be the same for 1. 0 and 1 are the only ones that are like that. And then we want to convert 0.23 to binary in the same way we did before, and we see that it comes out to this. So this is going to represent our mantissa, this is our exponent, and this is our sign. And then as we see here, we have 1 sign bit, 1 exponent bit, and then, so that's 2 bits, we have 32 total bits, which means we're going to have 30 bits for the fraction or the mantissa portion. We want to calculate our exponential bias. So we do 2 to the k minus 1. Our k is 1, so it's 2 to the 0. So it's 1 minus 1, which is equal to 0. Then we want to add our 1 exponent bit, which is 1, and then convert this number to binary, which again, 1 in decimal to binary is also 1. Once we do all that, we want to put it all together. We want to put together our sine, our exponential bias, and our mantissa. So just to recap, we have our sine here, 0, exponential bias, 1, and our mantissa here. It's this long number. So we want to put it all together, sine 0, exponential bias 1, then here's our binary point, and then we'll put our mantissa on the end. Now, after we add our mantissa, we're still only using 20 out of the 32 bits we have allocated. So we'll fill the remainder with zeros. So we have our sine, our exponential bit, or exponential bias, and then we have our mantissa here, and then we fill the rest with zeros, and that's how you represent 1.23 in decimal form into binary form using floating point notation. So just comparing the two, fixed point is very simple and fast. It's really easy to do, and you're working with a small number of bits, so it's a lot easier for computers to handle. And when you prefer speed over precision, it's better to use fixed point. But there's a lot of numbers that can never really truly be represented in fixed point, or even come even close. Numbers like 1/10, it'd be pretty hard to represent that in fixed point because you need a lot of decimal places to get to the really small values. Floating point is a lot more precise and accurate, but it's more difficult because the computer has to figure out how many bits to designate to each portion. But when you want precision over speed, you should use floating point. It's a lot easier to get the actual value, or at least get a lot closer to it, because you can go a lot further into the decimal portion. Or if you have a large whole number, you can have less bits for the decimal portion and have more in the exponent portion, and you can get closer there. So it's just much easier to represent really small or really large numbers, and it's a lot more precise than floating point, but it is a little bit slower and it's a lot more difficult for the computer to handle. So if you do prefer speed over precision, you want to use fixed. If you prefer precision, you want to use floating.